Yield lines, special cases. This video deals about square slabs loaded with one point load. The point load can be situated anywhere on the slabs, and its position is on the x direction d1 and on the y direction d2. It's a concentrated load P. We will first determine the axis of rotation, which is, of course, at the supports. We got 4 axes of rotation, and we got 4 intersections of those axes. So the yield lines start at the cross section, but because it is a point load, we use the rule of attracting yield lines. So the point load attracts the yield lines, and we have 4 yield lines like this. It's obvious that when P is too close to the edge, the yield lines are not realistic because the theta is too big, or the angle of rotation is too big. So I recommend that the value of D1 and D2 should be situated between 0.2a and 0.8a, so that you have at least a decent distance between the point load and the edge of the slab. Work done by the external forces, it's easy. The point load times is the unit value of the deflection delta, so it's P times delta. The work done by the internal forces is, of course, the plastic bending moment M multiplied by the projection on the rotation axis. So if you take, for instance, those two yield lines projected to this axis, it's A, and times the axis of rotation, which is delta, divided by the maximum distance, which is d1. So that is this. When we go now to this yield line, we project those yield lines to the axis. So it's A times delta divided by d2, which is this. Of course, for the others, projection on this side or on this side, the length here, it's A minus d1, and this is A minus d2. So we have this expression for the work done by the internal forces. Making E equal to D, we can get M, and M is then expressed as the point load divided by a coefficient beta, and beta is equal to this expression here, or like it's stated here. But we make it a little bit more easy to handle. We say that D1 is equal to alpha 1 times A, and D2 is alpha 2 times A. So it's just a dimensionless expression. Now we can make a graph of the maximum bending moments M in function of alpha 1 and alpha 2. So it's in fact in function of D1 and D2. We can draw this graph for P is the scale is that the load is 1. P is 1, so that's the scale for the bending moment. For other point loads, you just multiply this value with the load. And I've shown 4 different curves for different relationships. For alpha 2 equals 0.2 to 0.5, and alpha 1, 1.2 to 0.8. So we know that alpha 1 and alpha 2 must be situated in 0.2 to 0.8. The bending moment is given by the point load divided by beta, and beta is given by this nice expression. We see immediately that there the maximum is given for alpha 2 equals 0.5 and alpha 1 equals 0.5, and it gives you P over 1, not 0.125, so P over 8. So it's the point load divided by 8 is a maximum bending moment when the load is situated in the center of the slab, which is obvious. Now, just notice that we only have 4 different curves that we have plotted. Why did we not plot alpha 1 in function of 0.6 or and so on? Well, it's very simple. It's because of symmetry, of course. So the maximum bending moment of alpha 1, alpha 2 is exactly the same as alpha 1 or when alpha 2 is 1 minus alpha 2. So it's the same value for the bending moment because of the symmetry of the square slab. For the same for alpha 1, so the bending moment alpha 1, alpha 2 is equal to the bending moment of 1 minus alpha 1, alpha 2, or you can interchange alpha 1 and alpha 2, of course, so it does not make any difference. That's why we only have the 4 curves like here, because m alpha 1.8 is exactly the same as m alpha 1.2. So m is p over beta. Beta is equal to this expression. You can now, instead of plotting m for different values, you can now just plot the coefficient beta for the different values so that the bending moment is the point load divided by this number. And in function of alpha 1, and we know for alpha 2, we only need those curves. 1, 2, 3, 4. Okay. And then it's easy to see the smaller beta is the bigger m. So this is again our maximum. So the maximum is situated when the load is in the center of the slab. And it's given by P over 8. Notice again, this is independent of A. Very strange, but it's like that.